Okay, so moving on to the last 4 slides of our lecture. Here we're going to talk about the magnetic field on a loop of wire. So suppose you have a closed loop of wire with the magnetic field pointing across the plane of the loop. So let's visualize this. And so we're going to assume there's a current I in the loop. In fact, we'll make it rectangular because it'll be easier to see what's going on in this. And so this is the most basic example. So we have a magnetic field going straight across the plane of the loop. And so we have the current going across the loop. So what exactly is happening? So again, we're going to apply the right-hand rule in a few different places. So we have, we'll start with the portion of the current that's going up. You curl in the direction of the magnetic field, the force points into the board. On the top, the current and the magnetic field are pointing in opposite directions. That means F is equal to 0. And on the bottom, they're pointing in the same direction, so F is also equal to 0. But then you have on the bottom, and then pointing into the board, or rather the bottom and pointing to the right. And so the thumb points out of the board. So on this side, F points out of the board. So this is the overhead view. And then the side view, you have, call this the plane of the loop. You have an axis of rotation. So again, you have B pointing like this, and you have a force on one side and an opposite force on the other side, and what you're going to get is rotation. And we're going to define a line that's perpendicular to the plane of the loop, and so that the magnetic field, which is still horizontal or to the right in this vantage point, makes an angle theta with a line perpendicular to the plane of the loop, so that the torque is the force times distance. And so we'll make this length L, and then we'll have a width W that goes across. So that's the horizontal length. And so what you have then is that the torque is equal to the force, which is I times L times B. And so we have the width W like this. And that's times the sine of theta. And then the moment arm, or the distance from the axis of rotation to the point where the force is acting, is W over 2. But you're multiplying that by 2 because you have the same force acting in 2 different places. So you're doubling the force, and so you get I times L times W times B times the sine of theta. But L times W is just the area enclosed by the loop. So that becomes I times A times b times the sine of theta. And so that's the magnitude of the torque. And notice, because you have the sine of theta, you can write this as a cross product. So the torque is equal to I times the cross product of A and B. And so we're defining an area vector like we did when we talked about electric flux, so that it points perpendicularly outward from the surface. And and then that's cross B, where that's the magnetic field. And you can also write this as a new vector mu cross B. Well, what is mu? Mu is called the magnetic dipole moment. And so it's equal to I times the vector A. But you do have to specify direction with this. And so that's going to be shown on the next slide, that the direction is found by the right-hand rule number 2. So your fingers curl in the direction of I, whether it's clockwise or counterclockwise, and then the magnetic dipole vector points in the direction of mu. So we're giving it a direction, so it's pointing along the axis of rotation. But which way along the axis of rotation depends on which way the current is circling. Now, this is the principle behind electric motors. So you have a loop of current exposed to a magnetic field. You're going to, that current is going to rotate. And so it makes it possible to turn the wire, to turn a wheel. And so you have a loop of current exposed to a magnetic motion, or to a magnetic field, you can turn the wheel. The opposite of this is an AC generator, which we'll talk about in chapter 29. And in that case, you're turning the wheel where there's a loop of wire, and that's creating a current. And so it's sort of the same thing, but only in reverse. Now, when you have a loop of wire exposed to the magnetic field, there's a potential energy that's associated with it. And so the potential energy is negative mu dot B, or negative I times A times B times the cosine of theta, where again, theta is perpendicular to the magnetic field, and it's direction specific. So you're figuring out mu the same way. But the potential energy is minimized when the dipole moment vector lines up with the magnetic field. So this is what happens, going back to what we talked about at the beginning of the lecture in part 1 of this, or the first video for this, that when, for example, in iron, if you have a lot of moving or circling charges, or circling electrons to be specific, what'll happen if you expose them to a magnetic field, there will be a torque exerted on that loop of wire, on that rotating electron. And what happens is their dipole moments will wind up lining up with the magnetic field. And so this applies, at the macroscopic level with a loop of current, but also at the microscopic level if you have electrons. And so the potential energy is minimized, and a conservative force will act to minimize potential energy. Gravity brings objects down. Here the magnetic force acts the same way. It acts to minimize the potential energy. So you have stable equilibrium when the dipole moment vector is pointing in the same direction as the magnetic field. So let's go to 2 examples and we'll be done with the chapter. So this is number 36. It's on page 729. So a 13.0 centimeter diameter circular loop of wire is placed with the plane of the loop parallel to the uniform magnetic field between the pole pieces of the large magnet. Of a large magnet, excuse me. When 4.20 amps flows into the coil, the torque on it is 0.185 Newton meters, what is the magnetic field strength? So the plane is parallel to the loop, which is what where the torque is going to be maximum, because theta is going to be 90 degrees. So we have a circular loop, and so the magnetic field is going straight across the plane. We're given that the diameter equals 13.0 diameters, or 13.0 rather, centimeters. And you have a current going through the loop of 4.20 amps. And you're given that the magnitude of the torque that's generated by the magnetic force is 0.185 Newton meters. You can write it as meter newtons. They're equivalent to each other. So the torque is equal to I times A times B. And you don't need to worry about the sign of theta because magnetic field is parallel to the plane of the loop, which means it's perpendicular to a line that's perpendicular to the plane of the loop. So theta is 90 degrees and the sign of theta is 1. And again, theta is defined that way so that you can use the cross product, take advantage of the cross product formalism. So we're asked to find the magnetic field strength. So the magnetic field strength is equal to tau, which we're given, divided by I times A. We're given I, we're not given A directly, but we have enough information to figure out what A is. It's circular. So the area enclosed by a circular loop is just pi r squared. And we can figure out r from the diameter, but remember, we're not given the radius directly. So that's 0.185 Newton meters divided by I, which is 4.20 amps, times pi, and times the radius, which is 6.5 centimeters. So we can write that as 0.0650 meters. And again, we want to put everything in SI units, and don't forget we're squaring that. We want to put everything in SI units so that the answer is in SI units, or Tesla in this case. So that's 0.185 divided by 4.2 divided by, okay, so 0.185 divided by 4.2 divided by pi divided by 0.065 meters, and you're squaring that term. And you get a magnitude of, for the magnetic field, and this is to 3 significant figures with what we have, that's 3.32 Tesla. So that's the first of our examples. The second example we're going to go through says how much work is required to rotate the current loop. And so this is problem number 35. So figure 2722, in a uniform magnetic field from theta equals 0 to theta equals 180. So the figure is on a different page, but let's get back to the whiteboard. So the figure itself is on page 718. And so you have a horizontal magnetic field pointing to the right. You have the plane of a loop And so we'll draw a line perpendicular to the plane of the loop. And so it makes an angle theta with the magnetic field. And so the problem is asking, how much work is required to rotate the current loop in a uniform magnetic field from theta equals 0 to theta equals 180? So when theta equals 0, you have the plane of the loop like this. And so we'll draw this as the dipole moment vector. And so mu is like that. And then when theta equals 90, mu is like that, and b is like that, and then theta equals 180, just so you can visualize. And so b and mu are pointing in opposite directions when theta equals 180. And when theta equals negative 90 degrees, that means the dipole moment vector is pointing down. So that's what we're looking at. And the minimal potential energy is at theta equals 0. So we're asked for the work that's done in these configurations. And we're assuming the work is done by an external force. And so the work done is equal to delta K plus delta U. So an external non-conservative force. We're not told anything about the motion, so we're just going to assume speed or anything like that. So we're just interested in the change in potential energy. So, so for part A, the work done is equal to negative, and remember mu dot B, or the potential energy rather, let me rewrite that. The potential energy is equal to negative I A B cosine theta. So for part A, the work done is equal to the change in potential energy, which is, and we're in the first part, we're going from 0 to 180. So that's negative I A B cosine 180 degrees minus negative I A B cosine 0 degrees. So we're going from 0 to 180 degrees, and we want to figure out the change in potential energy. So we're increasing the potential energy. The cosine of 180 degrees is -1. The cosine of 0 is +1. So in both cases, you get double negatives that cancel out. So you have IAB plus IAB. So that becomes 2 IAB. And are we given in that case getting back to that, are we given values of IAB? The answer is no. So the work done flipping the loop to where the dipole moment aligns with the magnetic field to where it's completely opposite to the magnetic field, you're doing positive work because you're increasing the potential energy. So again, potential energy is minimized when the dipole moment vector and the magnetic field vector are in perfect alignment. So if you flip it around, they're in the opposite directions to each other. That's the state of maximum potential energy or unstable equilibrium. Basically, if you tilt it a little bit in either direction from that point and let it go, it will flip over. Whereas if it's oriented so that theta is equal to 0, the dipole moment and the magnetic field vectors are in alignment, and you tip it a little bit in one direction, it will go back to the stable equilibrium. So it will rotate back to theta equals 0. Now for part B, you're going from 90 to negative 90, I believe. But the cosine of theta in both cases is 0. So you're not actually changing the potential energy to do that. It's either going to gain or lose potential energy, at least to start, as you turn it. But once you turn it 90 degrees, as you turn it another 90 degrees, it's going to lose whatever potential energy it gained, or vice versa. So the work done going from 90 degrees to negative 90 degrees is 0. The work done going from 0 to 180 degrees is twice the magnetic dipole moment, or I times A, times the magnetic field. And so that's how you solve that problem. And that is it for chapter 27. The next chapter, which will come after the next exam, is chapter 28. And so we'll talk about the sources of magnetic fields. What we learned about in this lecture was that magnetic fields exert forces on currents and moving electrical charges. What we'll see in chapter 28 is that magnetic fields are also created by currents and by moving electrical charges. So thank you for now, and we will talk again soon.